What is z-scores? It is used to transform raw scores into more meaningful values and standardize a distribution and compare scores from different distributions. In other words, for example, let's look at this question. Suppose a student got scores of 400 on end of year test. How does he know if his score is good? You know, suppose that the population mean score for the test is 500 and the population standard deviation is 100. Now we know his score of 400 is below the mean, and we know that he was exactly one standard deviation below the mean. All these things, if the mean is 500 and if the distribution is like this, getting 400 points is below the average. And how much below? How many percentile? He belongs to. All these things you can calculate, and turn it into something like this. Making the midpoint 0 and the distribution that are higher than the midpoint, are going to be positive numbers, and distributions that are lower than the midpoint are going to be negative numbers. And that way you can tell, you are lower than easily tell. You can easily tell certain distributions are, lower or higher than the mean mean distribution. That's what the z-score is. And using the numbers like 1, 2, and 3 instead of raw numbers, that helps to compare different distributions. By turning raw scores into what we call z-score. By making standard deviation. Standard deviation can be anything in raw scores. In this case, it is 100. But by making standard deviations 1, it creates z-scores. That's what z-score is about. Okay, so suppose this distribution is normally distributed, and when you create a z-score distribution, what you do is adjusting the shape. I mean, not the shape, the values, so that the standard deviation is going to be 1. That's what the z-score distribution is all about. And that way you can compare, each distributions, each set of distributions, with any other sets of distributions. And in this example, this is how you calculate the z-score. What z-score is you can tell where in a distribution a certain score is located. And how you do it is z-score equals raw score minus population mean divided by standard deviation. And for example, in this previous example, population mean is 500, and this raw score of this particular distribution was 400, and 100 is a standard deviation, so it's -1, which means lower than the population mean by 1 standard deviation. So you just say it is one standard deviation below the mean. That's how you say it. Okay, suppose a second student got a score of 700 on the same test, and okay, how do you calculate the z-score for that student? Okay, that score. Okay, so z-score is, this is going to be 700, and the population mean is still 500, and the standard deviation is 100. So 100 and 700, so it's 2. So you can say this score is 2 standard deviation above the mean. Okay, it doesn't have to be, clear-cut numbers. 357. If you get 357, it's going to be 357 minus 500, and it's minus 1.43. And you say this score is 1.43 standard deviations below the mean. Okay, that's how you say. Okay, so z-scores tell us whether someone is above or below the mean, how many standard deviations someone is from the mean. If I transform all the raw scores in a distribution to z-scores, I will have a standardized distributions. I will have a standard normal distribution, a z-score distribution. The z-score distribution will have a mean of 0 and a standard deviation 1. So standardizing a distribution means creating a z-score distribution, z-distribution. And what z-score distribution is, you are making the mean 0 and making the standard deviation 1. And z-score distribution will have the same shape as the original distribution. Okay, z-score is a normal distribution. Z-scores can be particularly helpful to us when a distribution is normal. This is the point. When a distribution is normal, if a distribution is normal, we can determine the proportion of observations in a distribution that are below and above any z-score. Suppose a score on a given test are normally distributed with a mean of 500 and standard deviation of 100. Also, suppose a person scores 400 on a test. If we calculate the z-score, it's minus 1. So the person scored 1 standard deviation below the mean. What that means is this. So this person's score is right here in the distribution. That frequency is, so this many people got 400, and so it is less than majority. And what that means is that this many people got above 400, and this many people, or should I say this few people got below 400, and this many people got exactly 400. So you can tell a distribution or a proportion of people are distributions. So anyone who got below 400, the proportion of the people who got below 400 is this much, out of the entire population. And people who got a proportion of people who got above 400 is this much, right? Out of the entire population. And it's a z-score version of the proportion. And what's so good about z-score is that, why do you do that? Because you're getting the same shape and same proportion anyway. So z-score tells you, there's a table, z-score table, and you can tell by using the z-score, they create a table to show you how many, not, to tell you the exact proportion of this area. That's what the z-score table is. If you look at the z-score table, you can find the value for this proportion. So if the z-score is -1, then according to the table, it shows the proportion of this area in relation to the entire area. So here, see, it doesn't have it doesn't show -1 here, but let's say it's -2.0 or okay, so -2.0 here. See, proportion is 0.0228. That's the proportion. Proportion of this area is going to be, that. If the z-score is -2.12, for example, so -2.12 is going to be this number. So the proportion is going to be of this area is going to be -1.2, right? So it's 0.0170. That's going to be a proportion. So in other words, it's going to be about 1.7%, right, of the entire population. -0 z-score is proportion is 0.1587. So the proportion of students who score below that is 15.87% of people. That's what it is. See, this proportion of this area is going to be 0.1587. In other words, this area, larger area, is going to be okay, 0.8413, right? 8413, because the entire area is going to be 1, and this is going to be 0.1587. So we're gonna try to calculate all of these, and answer some of the questions about the distributions. Exercise.